Venus is the closest planet to Earth, nearly identical in size, almost the same mass, born from the same spinning disk of gas and dust, roughly 4.5 billion years ago, orbiting at distances so similar that for most of human history, people assumed the two worlds must be alike. Some early astronomers imagined tropical jungles beneath those bright white clouds. Others pictured oceans. A few even imagined civilizations. They were wrong about all of it. The surface temperature on Venus averages around 867 degrees Fahrenheit. That is hot enough to melt lead, hot enough to melt zinc, hot enough to glow a faint dull red in the permanent darkness beneath those clouds. The atmospheric pressure at the surface is 92 times what you feel standing at sea level on Earth, which is roughly equivalent to the crushing pressure you would experience 3,000 feet beneath the ocean. The atmosphere itself is 96.5% carbon dioxide, and the clouds that look so bright and inviting from Earth turned out to be made of sulfuric acid. When the Soviet Union managed to land a probe on the surface in 1982, a spacecraft called Venera 13, it survived for exactly 127 minutes before the planet destroyed it. That remains the longest any human-made object has ever functioned on Venus. 2 hours and 7 minutes, then silence. For decades after those early missions, the scientific consensus on Venus was straightforward and frankly, a little boring. Venus was a dead world, geologically dormant, atmospherically understood in broad strokes. A cautionary tale about greenhouse gases, sure, but not a place hiding surprises. The textbooks were written, the case was closed. Scientists turned their attention to Mars, to the outer moons, to the search for water ice on Europa and methane seas on Titan. Venus was yesterday's news, but in the last few years that certainty has collapsed. Discovery after discovery is rewriting what scientists thought they knew about Earth's closest neighbour. Active volcanoes erupting on the surface right now, a gas in the atmosphere that, on Earth, is produced almost exclusively by living things, a mysterious substance absorbing enormous amounts of solar energy that no one has been able to identify after nearly a century of trying. Lava tubes beneath the surface large enough to dwarf anything found on Earth or the Moon, and mounting evidence that billions of years ago, Venus may have had liquid water, oceans, moderate temperatures and conditions suitable for life. Something really weird is happening on Venus, and for the first time in decades the scientific world is paying attention. If you find this kind of deep exploration fascinating, consider subscribing. We go deep on topics like this regularly, and it helps us keep making them. Now, to understand why the recent discoveries are so extraordinary, you first need to understand what Venus actually is. Not the myths, not the assumptions, the planet itself. Venus is 7,521 miles across. Earth is 7,918. The difference is so small that if you could somehow place Venus next to Earth in space, they would look like near identical twins. Venus has about 81.5% of Earth's mass, and if you could stand on its surface without being immediately crushed and incinerated, you would weigh about 90% of what you weigh on Earth. The gravity would feel almost familiar. Your legs would work the same way. You could throw a ball and it would arc through the air in a trajectory that would seem perfectly normal. For a brief, disorienting moment, it might almost feel like home. But everything else about being on that surface would be profoundly, viscerally alien. The sky above you would be a thick yellowish haze. The clouds of sulfuric acid begin at roughly 30 miles up and extend to about 43 miles in altitude. Below those clouds, the atmosphere is so dense and so thick with carbon dioxide that it actually bends light. If you could somehow see through the haze, the horizon would curve upward in every direction, creating the unsettling illusion of standing at the bottom of a giant bowl. The sun if you could make it out at all, would be a vague, diffuse brightening in the sky. It would provide light, but very little of it. The surface of Venus exists in a kind of permanent dim orange twilight, and it is hot. Unimaginably, relentlessly, uniformly hot. The temperature barely changes between the equator and the poles. It barely changes between the side facing the sun and the side facing away. Day and night, pole to equator, the temperature hovers around that same 867 degrees. The greenhouse effect on Venus is the most extreme example in our entire solar system. Carbon dioxide traps heat. More heat evaporates more material. More material in the atmosphere traps more heat. On Venus, this feedback loop ran to its absolute extreme and never stopped. The structure of Venus's atmosphere is as layered and complex as any feature of the planet. It is not a uniform blanket of gas. It is a stratified system with distinct zones, each with its own character, its own chemistry, and its own mysteries. At the very top, above roughly 60 miles, is the upper haze layer, a thin zone of fine sulfuric acid particles that scatters sunlight and gives Venus its brilliant white appearance from space. Below that, between roughly 43 and 37 miles, lie the upper clouds, where the mysterious ultraviolet absorber does its work, capturing solar energy and driving atmospheric dynamics. The middle clouds, between about 37 and 33 miles, are the densest part of the cloud system, thick with sulfuric acid droplets that range from sub-micrometer particles to the large non-spherical mode-free particles that remain unidentified. The lower clouds between 33 and 30 miles are thinner and transition into a haze that extends down to about 20 miles. Below the haze, the atmosphere is clear but extraordinarily dense, a column of nearly pure carbon dioxide, so thick that it becomes almost fluid-like near the surface. The temperature profile follows a gradient that is, in its broad strokes, predictable by physics but remarkable in its extremes. At the cloud tops around 43 miles altitude, temperatures are approximately minus 45 degrees Fahrenheit, cold enough to freeze the sulfuric acid droplets, descend to 37 miles within the cloud layer, and the temperature climbs to roughly 170 degrees Fahrenheit. At 30 miles, where the clouds thin, it reaches roughly 350 degrees. Continue downward and the temperature climbs relentlessly, passing 500 degrees around 18 miles, 700 degrees around 9 miles, and finally reaching that brutal 867 degrees at the surface. The temperature increases smoothly and predictably, following what physicists call the adiabatic lapse rate, the rate at which temperature increases with increasing pressure in a gas. Venus's atmosphere is remarkably well mixed and thermally stable below the clouds. There are no weather systems, no fronts, no storms near the surface. The air is hot and still and dense and essentially motionless. All of the atmospheric action, all of the wind and turbulence and dynamic behaviour occurs in and above the cloud layers, and within those clouds the behaviour is extraordinary. In addition to the super-rotation winds that circle the planet in 4 days, the atmosphere exhibits enormous Y-shaped and V-shaped cloud patterns visible in ultraviolet images. These patterns are created by a combination of the Hadley cell circulation, which carries air from the equator toward the poles, and the super-rotation itself, which stretches and distorts the cloud features into their distinctive shapes. The patterns shift and evolve on timescales of days, giving Venus a dynamic, living appearance when viewed in ultraviolet light that stands in stark contrast to its featureless white orb at visible wavelengths. The European Space Agency's Venus Express spacecraft discovered something else in the atmosphere that added yet another layer of mystery. In 2011, it detected a phenomenon called the Venus Glory, a rainbow-like circular pattern of light that appears when sunlight is scattered by cloud droplets directly back toward the observer. Glories are common on Earth. You can see them from an airplane when sunlight reflects off a cloud layer below you, creating a circular ring of colours centred on the aircraft's shadow. The physics requires spherical droplets of a specific size range. On Venus, the glory was observed at the cloud tops, and its characteristics were consistent with cloud droplets that were mostly sulfuric acid, but appeared to contain a small fraction of something else, an unknown component that affected the droplet's refractive index. The researchers could not identify what the contaminant was. It may be related to the unknown ultraviolet absorber. It may be something else entirely. But it added another data point to the growing collection of atmospheric observations that refuse to be explained by simple sulfuric acid chemistry. Below the cloud layer, in the deep atmosphere near the surface, conditions become genuinely alien in ways that are difficult to convey with numbers alone. At roughly 30 miles above the surface, the atmospheric pressure is about 10 atmospheres, roughly the pressure experienced by a scuba diver at 300 feet below the ocean surface. By 15 miles altitude, the pressure has climbed to about 30 atmospheres. Near the surface at 92 atmospheres, the carbon dioxide atmosphere is so dense that it is technically no longer a gas in the ordinary sense. It exists in what physicists call a supercritical state, a condition where the distinction between liquid and gas breaks down. Supercritical carbon dioxide has the density of a liquid but the viscosity of a gas. It fills spaces and flows like a gas, but carries the dissolving power and heat transfer properties of a liquid. Walking on the surface of Venus, if such a thing were possible, would feel less like walking through air and more like wading through a warm, invisible fluid. Objects on the surface would be buoyed slightly by the dense atmosphere. Sounds would travel differently, faster and with less attenuation, which is why the Venera 13 microphone could pick up the faint wind despite its low speed. This is the environment that the Soviet landers entered, the Da Vinci probe will traverse, and that any future surface mission must survive. Understanding it is essential not just for engineering purposes, but because the atmosphere of Venus is not merely a barrier to exploration. It is, in many ways, the most scientifically interesting feature of the entire planet. Venus also has one of the most peculiar rotations of any planet. A single day on Venus, measured from one sunrise to the next, takes 243 Earth days. Its year, one complete orbit around the Sun, takes only 225 Earth days. Venus's day is longer than its year. And to make things even stranger, Venus rotates backward. If you could float above the North Pole of Venus and watch, the planet would be spinning clockwise, the opposite direction of Earth and most other planets in the solar system. Scientists call this retrograde rotation. The leading theory is that something massive, perhaps a planet-sized object, slammed into Venus early in its history and either flipped its rotation or slowed it so dramatically that gravitational interactions eventually reversed it. But the truth is, no one knows for certain why Venus spins the way it does. Venus's slow rotation has another consequence that is, in many ways, just as significant as the strange day-night cycle. It explains one of the planet's most critical missing features, a global magnetic field. Earth generates its magnetic field through a process called the geodynamo. Deep inside our planet, the outer core is made of liquid iron and nickel. Earth's rotation creates what physicists call the Coriolis effect within this liquid metal layer, organising the convective currents into patterns that sustain a powerful magnetic field extending tens of thousands of miles into space. This magnetosphere acts as an invisible shield, deflecting charged particles from the solar wind, the constant stream of high-energy protons and electrons that the Sun flings outward in all directions. Without the magnetosphere, the solar wind would gradually strip away Earth's atmosphere, molecule by molecule over billions of years. Mars, which lost its global magnetic field roughly 4 billion years ago, provides a cautionary example. Its atmosphere has been slowly eroded by the solar wind ever since, leaving the planet with surface pressure less than 1% of Earth's. Venus has a core that is likely similar in composition to Earth's, a ball of iron and nickel roughly 2,000 miles across. But Venus rotates so slowly that the Coriolis forces within the core are negligible. Without sufficient rotation to organize the convective currents in the liquid outer core, the geodynamo process cannot sustain itself. The result is that Venus has no global magnetic field. Not a weak one, essentially none at all. The magnetic field strength at Venus's surface is less than 1/10,000th of Earth's. This should have been catastrophic. Without a magnetosphere, Venus's atmosphere should have been vulnerable to the same solar wind stripping that thinned Mars's atmosphere to near nothing. And yet Venus has the thickest atmosphere of any rocky planet in the solar system. Its atmospheric pressure is 92 times Earth's. It has more atmosphere, not less. The solar wind has been pounding Venus for 4.5 billion years with essentially no magnetic protection, and the atmosphere is still there, massive and dense and showing no signs of significant depletion. How is this possible? Part of the answer lies in Venus's induced magnetosphere. When the solar wind encounters Venus, it interacts directly with the upper atmosphere rather than being deflected by a magnetic field. This interaction creates electric currents in the ionosphere, the layer of electrically charged particles in the upper atmosphere, which in turn generate a weak but significant magnetic barrier. This induced magnetosphere is not as effective as Earth's intrinsic field, but it provides enough deflection to prevent the solar wind from directly impacting the bulk of the atmosphere. The dense atmosphere itself also plays a role. Even if the solar wind strips away molecules from the very top of the atmosphere, the sheer mass of gas below provides an enormous buffer. Removing a significant fraction of Venus's atmosphere through solar wind erosion would require timescales far longer than the age of the solar system. But the lack of a magnetic field has another consequence that may be even more important for the question of Venus's habitability. On Earth, the magnetic field protects the surface from solar ultraviolet radiation only indirectly, by preserving the ozone layer that absorbs most of the harmful UV, but the magnetic field's primary role is protecting the atmosphere itself. On Venus, without that protection, ultraviolet radiation penetrates deeper into the atmosphere and reaches the cloud layer with greater intensity. This UV radiation is what drives the photodissociation of water vapor, breaking water molecules into hydrogen and oxygen, allowing the lightweight hydrogen to escape to space. If Venus ever had surface water, the absence of a magnetic field would have accelerated its loss. The very feature that failed to protect Venus's water, its slow rotation eliminating the magnetic field, may have been the mechanism by which that water was ultimately destroyed. This creates a deeply interconnected chain of cause and effect. Venus rotates slowly, possibly because of a massive ancient impact, possibly because tidal forces from a former ocean braked its spin. The slow rotation prevents the generation of a magnetic field. Without a magnetic field, the upper atmosphere is exposed to intense solar wind and ultraviolet bombardment. The UV radiation breaks apart water molecules. The hydrogen escapes. The water is lost forever. And without water, the carbon cycle cannot operate. Carbon dioxide accumulates. The greenhouse effect runs away, and the planet becomes the furnace it is today. Every feature of Venus connects to every other feature. Pull one thread, and the entire tapestry shifts. Understanding any single aspect of Venus in isolation is almost impossible. The planet demands to be understood as a system each component influencing and being influenced by all the others. This interconnectedness is part of what makes Venus so scientifically compelling and so challenging to study. It is also part of what makes it so relevant to understanding Earth, which operates as an equally interconnected system but has managed so far to keep all of its feedback loops running in the right direction. The history of human exploration of Venus is in many ways a history of ambition and meeting brutal reality. The first spacecraft to successfully visit another planet was Mariner 2, a NASA probe that flew past Venus in December 1962. It carried no cameras. It didn't need them for its primary mission. Its instruments measured the temperature of Venus's surface from afar, and the readings were devastating for anyone who had imagined a habitable world beneath those clouds. The surface was blisteringly hot. The dream of Venusian jungles died that day. The Soviet Union took it further. Between 1970 and 1985, the Venera program became one of the most audacious campaigns in the history of space exploration. Venera 7, which landed in December 1970, was the first spacecraft to successfully land on another planet and transmit data back. It survived for about 23 minutes. Venera 9, landing in October 1975, returned the first photographs ever taken from the surface of another planet. The images showed a landscape of flat, broken rock stretching to the horizon under that dim orange sky. Venera 13, landing in March 1982, achieved the record: 127 minutes of operation, during which it transmitted colour photographs, analysed soil samples, and recorded the sound of the Venusian wind. The audio is available online. It sounds like a low, constant moan. The wind speed was only about 2 miles per hour, but the atmosphere is so dense that even that gentle breeze carried tremendous force. The engineering required to land on Venus and survive for even those few minutes deserves its own moment of appreciation, because it reveals just how hostile this environment truly is. Every Venus lander built by the Soviet Union was, essentially, a pressure vessel designed to resist conditions more extreme than any environment on Earth's surface. The later Venera probes were constructed from titanium and other high-strength alloys, with hulls thick enough to withstand the 92 atmosphere surface pressure. Inside the hull, the electronics were surrounded by thermal insulation, typically layers of high-temperature insulating materials designed to slow the transfer of heat from the exterior to the delicate instruments within. There was no active cooling, no air conditioning, no refrigeration system compact and reliable enough to operate in that environment for more than a few hours. The strategy was purely passive: insulate the interior as thoroughly as possible and hope that the instruments could complete their measurements before the internal temperature rose beyond what the electronics could tolerate. The descent itself was equally brutal. Each probe entered the atmosphere at speeds of roughly 25,000 miles per hour. A heat shield absorbed the initial deceleration, reaching temperatures comparable to those experienced by spacecraft returning to Earth. Then a series of parachutes deployed to slow the descent through the upper atmosphere. But here was the problem. Venus's atmosphere is so thick that parachutes work too well. If the lander descended slowly on parachutes all the way to the surface, the hours-long journey would expose it to the punishing heat for far too long, and the electronics would be dead before the probe ever reached the ground. So at a certain altitude, typically around 30 miles up, the parachutes were jettisoned and the probe fell freely through the dense lower atmosphere. The atmosphere itself provided enough drag to slow the descent to a survivable impact speed, roughly 15 to 20 miles per hour, without any parachute at all. The air on Venus is so thick that falling through it is more like sinking through a warm fluid than falling through a gas. The Venera 13 images, when they were finally transmitted back to Earth, showed a landscape that was both desolate and strangely familiar. Flat slabs of rock, broken and layered, stretched in every direction beneath that thick yellow sky. The rocks appeared to be basaltic, similar in composition to the volcanic rock that forms the ocean floors on Earth and covers much of Hawaii and Iceland. Chemical analysis of soil samples, collected by a small drill that extended from the lander and deposited material into an onboard X-ray fluorescence spectrometer, confirmed this. The surface of Venus is largely made of basalt, the same rock that forms from the cooling of iron-rich and magnesium-rich lava on Earth. The similarity of the surface chemistry was, in its own way, as remarkable as the differences in atmosphere. The ingredients were the same. The outcomes could not have been more different. One particularly memorable detail from the Venera 13 mission has become a piece of space exploration folklore. When the lander deployed its soil sampling drill, it was designed to collect a sample from the Venusian surface and deliver it to the analysis instrument. But when engineers later examined the images, they noticed something unexpected. The ejected lens cap from one of the cameras had landed directly in the spot where the drill was supposed to sample. There has been debate over the decades about whether the drill actually sampled the lens cap instead of the Venusian soil, though most engineers who have analysed the data believe the drill successfully reached past the cap to the surface beneath. Regardless of the outcome, the incident is a reminder of the extraordinary improbability of the entire endeavour. Humans launched a machine across 160 million miles of space, dropped it through an atmosphere of sulfuric acid, and attempted to drill into rock on a surface hot enough to melt lead, all while operating on a timer measured in minutes. That it worked at all remains one of the most impressive feats in the history of engineering. After Venera 13 and 14 in 1982, the Soviet Union sent 2 more landers as part of the Vega program in 1985. The Vega missions had a dual objective. The landers would study Venus's surface while the spacecraft continued onward to intercept Halley's Comet. The Vega landers survived about an hour each, but the program also deployed something unprecedented. 2 balloons into Venus's atmosphere. Each balloon floated at an altitude of roughly 34 miles within the cloud layer and drifted with the winds for about 46 hours, transmitting data on temperature, pressure, wind speed, and light levels as it travelled. The balloons covered over 7,000 miles during their operational lifetime, carried along by the super-rotating atmosphere. They provided the first sustained measurements of conditions inside Venus's cloud layer, the very region that, decades later, would become the focus of the Phosphine debate. No spacecraft has entered Venus's atmosphere since those Vega balloons in 1985. That is a gap of more than 40 years. The next probe to descend through those sulfuric acid clouds will be Da Vinci, carrying instruments unimaginably more sophisticated than anything the Soviets deployed. But it will face the same fundamental challenge. The clock starts ticking the moment you enter Venus's atmosphere, and Venus does not negotiate extensions. After the Venera and Vega missions, the Soviet Union's Venus program ended. The United States launched Magellan in 1989, which entered Venus orbit in 1990 and spent 4 years mapping 98% of the planet's surface using synthetic aperture radar. Radar can penetrate the dense clouds that visible light cannot. Magellan revealed a world dominated by volcanic plains, vast flat expanses of basalt, pockmarked with thousands of volcanic structures, shield volcanoes, pancake domes, lava channels stretching for thousands of miles, longer than any river on Earth. Scientists estimated that somewhere between 300 and 500 million years ago, Venus experienced a catastrophic resurfacing, event in which volcanic activity paved over most of the planet's surface in fresh lava. The relatively low number of impact craters confirmed this. The surface was young, geologically speaking. But was Venus still active? Magellan couldn't tell for certain. The mission ended in 1994 when the spacecraft was deliberately crashed into Venus's atmosphere. After that, NASA didn't send another mission. The European Space Agency launched Venus Express in 2005, which studied the atmosphere until 2014 and returned extraordinary data about cloud dynamics and chemical composition. Japan's Akatsuki orbiter, which entered Venus orbit in 2015 after a dramatic second attempt, has studied the atmosphere's wind patterns and thermal structure. And that, until very recently, was the state of Venus science. We had mapped the surface, we had sampled the atmosphere, we had measured the temperature and the pressure and the chemical composition, and the consensus was clear. Venus was a hellish, hostile world, interesting as a geological curiosity, important as a lesson in planetary climate, but fundamentally understood, not a place where surprises were expected. The textbooks said Venus was settled science. The textbooks were wrong. The first crack appeared in 2020, and it sent shockwaves through the entire planetary science community. But that story requires its own telling. Before we get there, it is worth understanding just how confident scientists were in their picture of Venus. Confident enough that NASA did not fund a dedicated Venus mission for over 3 decades. Confident enough that when proposals for Venus missions were submitted to the Discovery program, they were repeatedly passed over in favour of missions to Mars, to asteroids, to Jupiter's moons. Venus was the forgotten planet, the neglected twin. That confidence was built on data. Decades of it. Radar maps showing a surface dominated by volcanic plains with no clear evidence of ongoing eruptions. Atmospheric measurements showing a composition that could be explained, at least approximately, by known chemical processes. Temperature profiles that match theoretical models. Venus seemed to fit neatly into a box, a planet that had experienced a runaway greenhouse effect early in its history, lost its water, and settled into a stable, if extreme, equilibrium. There were a few loose threads if you looked carefully. The sulfur dioxide levels in Venus's upper atmosphere fluctuated in ways that were hard to explain without invoking active volcanism. Some thermal measurements from Venus Express hinted at hot spots on the surface near known volcanic structures. The composition of the lower clouds contained particles that didn't match any known substance. But these were footnotes, curiosities, not enough to upend the established picture. What changed everything was not a new mission. It was not a breakthrough telescope or a revolutionary instrument. What changed everything was scientists going back to the old data, with fresh eyes and new tools. Sometimes the most important discoveries come not from seeing something new, but from finally understanding what you were looking at all along. Venus orbits the Sun at an average distance of about 67 million miles. Earth orbits at about 93 million miles. The difference, 26 million miles, sounds significant. But in the scale of the solar system, where Jupiter orbits at 484 million miles and Neptune at 2.8 billion, Venus and Earth are practically neighbours. At their closest approach, they are separated by only about 24 million miles, closer than any other planet comes to Earth. You could fit roughly 30 Earths in the gap between the two worlds at closest approach. It is a very small number in cosmic terms. This proximity is part of why the divergence between Venus and Earth is so troubling. The two planets form from the same material. They are almost the same size. They orbit in similar regions of the solar system. Yet one became a world of oceans, moderate temperatures, plate tectonics, a magnetic field and abundant life. The other became a world where the air is hot enough to melt metal. The pressure would crush a submarine, and the rain is sulfuric acid that evaporates before it ever reaches the ground. Understanding why these two almost identical worlds ended up so dramatically different is not just an academic question. It is one of the most important questions in all of planetary science, because the answer tells us something about the conditions required for a planet to remain habitable, about the fragility of the systems that keep our world alive, about whether Earth's continued hospitality is a robust self-correcting certainty, or a delicate balance that could, under the right conditions, tip the other way. For decades the answer seemed simple. Venus was too close to the Sun. It received more solar energy. The extra heat evaporated its water early. The water vapour trapped more heat. The planet spiralled into a runaway greenhouse effect from which it never recovered. End of story. Next question. But recent discoveries suggest the story is not nearly that simple. Venus may have maintained habitable conditions for billions of years. The runaway greenhouse effect may have been triggered not by proximity to the Sun, but by internal planetary processes, and the current state of Venus's atmosphere contains chemical signatures that existing models cannot explain. The simple story was wrong. The real story is far more interesting, and it starts with volcanoes. But before we get there is one more thing worth appreciating about Venus. One more detail that makes the mystery of this planet so personal, so close to home. When you step outside on a clear evening shortly after sunset and look toward the western horizon, the brightest point of light in the sky is almost always Venus. It has been the brightest object in our sky after the sun and moon for as long as humans have existed. Ancient civilizations named it. The Babylonians called it Ishtar, after the goddess of love and war. The Greeks called it Phosphoros in the morning and Hesperos in the evening before realizing both lights were the same object. The Romans named it Venus, after their goddess of beauty. The Mayans tracked its movements with extraordinary precision and built their calendar partly around its cycles. For thousands of years, this brilliant light in the twilight sky was a source of wonder, of poetry, of navigation, of myth. And all that time it was a world that might have had oceans. We are so accustomed to thinking of Venus as hell that we sometimes forget how recently that picture formed. As late as the 1950s, serious scientific papers speculated about life on Venus. The clouds were thought to be water clouds, possibly hiding a warm, wet surface. Science fiction from that era is filled with Venusian swamps and Venusian oceans. It was only Mariner 2 in 1962 that shattered the dream. Before that, Venus was the planet most likely to harbour life, more likely than Mars, which was already known to be cold and dry. Venus was the hope. Then, in a single flyby, it became the nightmare. The emotional arc of our understanding of Venus mirrors something deeply human. A world of beauty revealed to be a world of horror. A twin that turned out to be something we could barely comprehend. And now, decades later, the possibility that the truth is more complicated than either extreme. That Venus was beautiful, and then it became horrible, and the transition between those two states may hold the key to understanding the long-term fate of every rocky planet orbiting every sun-like star in the galaxy. That is the scale of what is at stake in Venus science right now. The Magellan mission, which mapped the surface with radar in the early 1990s, gave scientists their most detailed look at Venus's geology. What it revealed was a surface unlike anything on Earth. There were no obvious plate boundaries, no subduction zones where one section of crust slides beneath another. Earth's surface is a dynamic patchwork of moving plates, and that movement drives everything from mountain building to ocean floor, spreading to the recycling of carbon through the planet's interior. Venus showed none of that. Instead, its surface appeared to be a single, unbroken shell of rock, what geologists call a stagnant lid regime. Heat from the planet's interior rather than being released gradually through plate tectonics, appear to build up until it erupted in massive volcanic episodes that resurfaced huge areas all at once. This mattered enormously for understanding Venus's history. On Earth, plate tectonics plays a critical role in the carbon cycle. Carbon dioxide from the atmosphere dissolves in rainwater, forms carbonic acid, weathers silicate rocks, and gets carried to the ocean floor, where it is eventually subducted back into the mantle. This process acts as a thermostat, regulating the amount of CO2 in the atmosphere over millions of years. On Venus, without plate tectonics, this thermostat does not exist. Carbon dioxide released by volcanoes stays in the atmosphere permanently. Over time, it just accumulates, and accumulates, and accumulates. Magellan also revealed the sheer scale of volcanism on Venus. The planet has more volcanic structures than any other body in the solar system. Over 1,600 major volcanic features have been catalogued, along with hundreds of thousands of smaller ones. Some are enormous. Mount Mons, near the equator, rises over 5 miles above the surrounding terrain. Theia Mons, in a region called Beta Regio, is even taller. The lava channels on Venus include one, Baltis Vallis, that stretches for over 4,200 miles, making it the longest known channel of any kind on any planet. By comparison, the Nile, the longest river on Earth, is about 4,130 miles, but the volcanic plains and enormous shield volcanoes were not even the most unusual features Magellan revealed. Venus has geological structures that exist nowhere else in the solar system, formations so strange that geologists had to invent new vocabulary to describe them. The most distinctive are the coronae. These are roughly circular to oval structures, typically between 60 and several hundred miles across, defined by concentric rings of ridges and fractures surrounding a raised or depressed interior. Venus has at least 500 of them. Nothing like them exists on Earth, the Moon, Mars, or any other body we have studied. The leading explanation is that corona form when plumes of hot rock rise from deep in Venus's mantle and push against the underside of the crust. The rising plume heats and lifts the surface, creating the central dome. As the plume spreads outward, it drags the crust with it, creating the ring of fractures. When the plume eventually weakens and the hot material cools, the center can collapse, leaving a depression ringed by the scars of its formation. The entire process is driven by heat escaping from Venus's interior, and the fact that Venus has so many coronae suggests that mantle plumes are a primary mechanism by which the planet releases its internal heat, compensating, at least partially, for the absence of plate tectonics. Then there are the pancake domes. These are flat-topped, steep-sided volcanic structures, typically about 15 miles across and less than half a mile tall. They look, from above, almost exactly like pancakes dropped onto a griddle. They form when extremely viscous lava, thick and slow-moving, oozes out of a vent and spreads outward under its own weight without flowing very far. On Earth, the closest equivalent would be lava domes like those found at Mount St. Helens, but Venus's pancake domes are vastly larger. The dense atmosphere may play a role. The high surface pressure on Venus slows the cooling of lava and suppresses the release of dissolved gases, both of which would keep the lava flowing for longer and allow it to spread more evenly before solidifying. They are, in their own quiet way, another reminder that geological processes on Venus operate by different rules than those on Earth, even when the underlying chemistry is similar. And then there is the tessera terrane. These are among the oldest surfaces on Venus, patches of intensely deformed rock that survived the global volcanic resurfacing event that paved over most of the planet's crust. Tesserae, the plural form, are characterized by intersecting networks of ridges and grooves, folded and fractured and compressed into patterns so complex that they resemble crumpled fabric viewed under a microscope. They cover roughly 7% of Venus's surface and are found almost exclusively on highland plateaus, elevated regions that stand above the surrounding volcanic plains like islands above a frozen sea. The tesserae matter because they are old, older than the plains, older than most of the volcanic features. They preserve a record of geological processes that occurred before the catastrophic resurfacing event, possibly billions of years before. If Venus ever had plate tectonics, if it ever had processes analogous to Earth's continental drift and mountain building, the tesserae are where the evidence would survive. Some geologists have noted that certain tessera formations resemble the fold and thrust belts found on Earth, where continental plates collide, such as the Himalayas or the Appalachians. Others argue that the deformation patterns are more consistent with localized compression and extension driven by mantle plumes rather than plate motion. The debate remains unresolved, largely because the resolution of Magellan's radar images, while groundbreaking for the 1990s, is not sufficient to distinguish between these competing models. This is one of the reasons the upcoming Veritas and Envision missions are so eagerly anticipated. Their radar instruments will image the tessera terrain at resolutions 10 to 100 times finer than Magellan achieved, potentially revealing structures that could settle the question of whether Venus ever had moving plates. There is something almost poignant about the tesserae. They are fragments of a planet that no longer exists, windows into Venus's deep past, preserved by the accident of their elevation, standing above the lava flows that erased everything else. Whatever secrets they hold about Venus's early geological history, about whether the planet once operated more like Earth, they have been waiting patiently in the Venusian darkness for billions of years. We are only now building the instruments capable of reading them, but Magellan's radar images, stunning as they were, captured a single snapshot. A photograph, essentially, of Venus's surface taken between 1990 and 1992. To determine whether the volcanoes were still active, scientists would have needed to compare images taken at different times. Magellan did orbit Venus for 4 years, and it did image some areas more than once, but the resolution and coverage were limited. And after Magellan, no one went back to look. For 3 decades, those radar images sat in archives. Scientists used them, students studied them, papers were written about them. But the question of whether Venus was still volcanically active remained open, and with no new missions planned, it seemed like it would stay that way for a long time. Then someone went back to the old data with a new question, and what they found changed everything. It is worth pausing here to appreciate just how much of science works this way. The data had been sitting there for 30 years, publicly available, accessible to anyone with the right tools and the right question. The volcanoes on Venus did not suddenly start erupting in 2023. They had been erupting all along. We just had not realized we already had the evidence. This is a recurring theme in the Venus story. Not that the planet is hiding its secrets from us, but that we have been too quick to assume we already know the answers, too quick to close the book, too confident in models that turned out to be incomplete. The data was always there. The phosphine was always there. The UV absorber was always there. The chemical anomalies were always there. What changed was not Venus. What changed was our willingness to look more carefully. And what we found when we looked more carefully is one of the most extraordinary stories in modern planetary science. A story about a world we thought we understood. A world that turned out to be far more alive, far more mysterious and far more relevant to our own future than anyone had imagined. It begins with a volcano named Ma'at Mons, and it begins not in the present, but in a set of radar images taken in 1991 by a spacecraft that had been dead for 3 decades, revealing an eruption that no one noticed until 2023. Scientists had always suspected Venus might still be volcanically active. The planet has a thick, hot interior. Its surface is relatively young, geologically speaking only about 300 to 500 million years old, based on great accounts. And the sulfur dioxide levels in the upper atmosphere fluctuated over time in ways that were difficult to explain without active volcanic eruptions pumping fresh gas into the sky. But suspecting something and proving it are very different things, especially when the surface of the planet in question is hidden beneath a permanent blanket of sulfuric acid clouds and the last detailed observations are 3 decades old. Proving volcanic activity on Venus required one of 2 things: either a new mission with instruments capable of detecting active eruptions in real time, or someone clever enough to find evidence that had been hiding in the old data all along. There were tantalizing hints over the years. The Venus Express orbiter, operated by the European Space Agency between 2005 and 2014, detected localized hotspots on the surface near known volcanic structures. Aydın Mons, a large volcano in the southern hemisphere, showed elevated thermal emissions that some scientists interpreted as evidence of recent or even ongoing lava flows. But the data was ambiguous. The hotspots could have been explained by variations in rock composition or surface texture rather than fresh lava. Scientists debated the findings. No consensus was reached. The sulfur dioxide measurements were also suggestive. Pioneer Venus, orbiting in the late 1970s and early 1980s, measured sulfur dioxide concentrations in the upper atmosphere that were significantly higher than what Venus Express measured decades later. Something had pumped a large amount of SO2 into the upper atmosphere sometime before or during the Pioneer Venus mission, and the levels had been declining since. The most natural explanation was a volcanic eruption, but it could also have been atmospheric circulation and patterns redistributing existing sulfur dioxide. Without direct evidence of surface change, the question remained open. Robert Herrick, a planetary scientist at the University of Alaska Fairbanks, was the one who finally closed it, and he found the answer entirely by accident. Herrick was part of the science team preparing for NASA's Veritas mission, a future Venus orbiter that would use advanced radar to map the surface at much higher resolution than Magellan had achieved. To test what Veritas might be capable of detecting, Herrick decided to go back to the Magellan Delta and look for surface changes. Magellan had imaged some areas of Venus multiple times during its 4-year mission, and Herrick reasoned that if any eruptions had occurred during that window, they might show up as differences between the earlier and later images. He started comparing radar images of areas near known volcanic structures. It was painstaking work. The Magellan images were taken from different angles on different orbits, which meant the same surface features could look slightly different, simply due to changes in viewing geometry. Herrick had to account for all of those factors before he could identify genuine surface changes. And then, at a volcano called Map Mons, one of the largest on Venus, rising about 5 miles above the surrounding plains near the equator, he found something unmistakable. In a radar image taken in February 1991, a volcanic vent on the northern flank of Ma'at Mons appeared nearly circular, covering less than 1 square mile. When Herrick compared it to another image of the same area taken in October 1991, just 8 months later, the vent had changed dramatically. It had expanded, its shape had become irregular, and the surrounding terrain showed features consistent with lava overflow, fresh rock flowing outward from the vent in a pattern that could only be explained by a volcanic eruption. Herrick and his colleague Scott Hensley ran computer simulations to rule out alternative explanations. Could the changes be artifacts of the different viewing angles? No. The geometry had been accounted for. Could it be a landslide or collapse? The modelling showed that the pattern of changes was inconsistent with collapse and entirely consistent with a volcanic eruption. The vent had not just changed, it had erupted, lava had flowed. The findings were published in Science in March 2023. It was the first direct observational evidence that volcanic eruptions had occurred on Venus in the recent geological past. Not millions of years ago, not during some ancient resurfacing event, during the same window that Magellan was orbiting, within a period of 8 months. To put the scale in perspective, the eruption at Mart Mons was comparable in size to the 2018 eruption of Kilauea on the Big Island of Hawaii, which destroyed over 700 homes and reshaped miles of coastline. And an eruption of that magnitude had occurred on Venus, while a NASA spacecraft was watching, and nobody noticed for 32 years. This raises a fascinating and slightly uncomfortable question about how we do planetary science. The data was public. It had been available for 3 decades. Any scientist in the world could have accessed the Magellan images and performed the same comparison, but no one had thought to look in quite this way, or at least no one had followed through with the systematic, image-by-image comparison that Herrick performed. The eruption didn't hide from us. We simply did not look carefully enough. It is a humbling reminder that even in an age of advanced instruments and enormous data sets, sometimes the most important thing a scientist can do is sit down, look closely, and ask the right question. The reaction in the scientific community was electric. Planetary scientists had long argued that Venus was probably still active, but there is a vast difference between probably and definitely. Herrick's discovery turned a reasonable hypothesis into an observed fact. Venus is volcanically active, the volcanoes are alive, and the method of discovery was almost as remarkable as the discovery itself. Herrick had not used some cutting-edge new instrument. He had not processed data with a revolutionary algorithm. He had done something far simpler, and in a way far more important. He had looked carefully. He had gone through the old images, one by one, comparing them methodically, asking a question that no one had taken the time to ask systematically before. Did anything change? The answer was yes, and the implications rippled outward in every direction. If Mart Mons had erupted during the 8 months between Magellan's observations, what else had erupted? Magellan orbited Venus for 4 years. It imaged about 98% of the surface, but it didn't image every area at multiple times. The overlap, the areas where images taken at different times could be directly compared, covered only a fraction of the total surface, and within that fraction, Herrick had only examined a small subset, focusing on areas near the largest known volcanic structures. The eruption at Mart Mons might be one of many that occurred during Magellan's mission, perhaps dozens, perhaps more. There was another implication, one that scientists found both exciting and unsettling. If Venus is erupting now, and if it was erupting during Magellan's mission in the early 1990s, then the volcanic activity is not a rare, isolated event. It is ongoing, it is persistent, and it is shaping the planet's atmosphere and climate in real time. Volcanic eruptions on Venus release sulfur dioxide into the atmosphere. Sulfur dioxide is a key component of the sulfuric acid clouds that blanket the planet. Observations from the European Space Agency's Venus Express Orbiter showed that sulfur dioxide levels in the upper atmosphere dropped dramatically between 2007 and 2014, a decline that puzzled scientists at the time. One explanation that now seems increasingly plausible is that a major volcanic eruption before Venus Express arrived pumped a large pulse of SO2 into the upper atmosphere, and what the spacecraft observed was the slow chemical processing and settling of that pulse over the following years. If correct, it means the atmosphere of Venus is not in a static equilibrium. It is being actively stirred and refreshed by volcanic activity on a time scale of years to decades. Volcanic eruptions also release carbon dioxide, the primary greenhouse gas in Venus's atmosphere. On Earth, volcanic CO2 emissions are balanced by the carbon cycle, which removes carbon through weathering and ocean absorption. On Venus there is no such balance. Every molecule of CO2 that a Venusian volcano releases into the atmosphere stays there. Over billions of years, this one-way process has contributed to the extreme greenhouse effect that keeps the surface at 867 degrees. And if the volcanism is ongoing, it means the greenhouse effect is not just a relic of Venus's past. It is being actively maintained and potentially strengthened right now. In 2024, an Italian research team led by David Sulcanese at the University of D'Annunzio in Pescara, Italy, decided to apply a similar approach to other parts of Venus's surface. They used a technique focused on radar backscatter analysis, examining how the radar signal reflected off the surface at different times. Fresh lava flows have a different radar signature than older weathered rock. When molten basalt cools and solidifies on the surface of Venus, the resulting rock has a rougher texture and a higher dielectric constant than the surrounding terrain that has been exposed to the corrosive atmosphere for millions of years. This difference shows up clearly in radar data. By comparing the backscatter data from different Magellan orbits, Sulcanese and his colleagues could identify areas where the surface properties had changed in ways consistent with fresh lava deposition. The technique required extraordinary precision. They had to account for differences in viewing geometry, local topographic effects, and the inherent noise in decades-old radar data. But the signal, when they found it, was unmistakable. They found two more eruption sites. The first was at Sif Mons, a large shield volcano in a region called Isla Reggio. Comparing data from 1990 and 1992, the team identified a new lava flow covering approximately 12 square miles of the surface. That is an area large enough to fill roughly 36,000 Olympic swimming pools with rock. The flow had distinct boundaries and radar properties consistent with freshly solidified basalt. It had not been there in the earlier data. Something had erupted between the two observation periods. The second site was in western Niobe Planitia, a broad volcanic plain in the northern hemisphere. Here the new lava flow was even larger, covering approximately 17 square miles, equivalent to about 54,000 Olympic swimming pools. For comparison, the 2022 eruption of Mauna Loa in Hawaii, one of the most closely watched volcanic events in recent history, produced enough lava to fill roughly 100,000 pools. The Venus eruptions were not trivial. They were substantial volcanic events, producing significant amounts of fresh rock across wide areas. The findings were published in Nature Astronomy in 2024, and Sulcanese's team made a point that sent a chill through the planetary science community. They had only analysed about 16% of Venus's surface. The vast majority of Magellan's data had not yet been examined for evidence of volcanic change. If 3 eruptions had been found in a relatively small sample, the total number of eruptions that occurred during Magellan's 4-year mission could be much higher. Venus might not just be active, it might be very active, potentially as active as Earth. The team put it simply in their paper. Their results suggest that Venus may be far more volcanically active than previously thought. The volcanic activity could be comparable to what we see on our own planet. Think about what that means for a moment. Earth is the most volcanically active rocky planet we know of. About 1,350 potentially active volcanoes dot the surface. On average, somewhere between 50 and 70 erupt each year. Volcanic activity drives plate tectonic, shapes continents, creates ocean floors, and influences the composition of the atmosphere over time scales of millions of years. If Venus has a comparable level of volcanic activity, but without plate tectonics to recycle the gases, then every eruption adds to the atmosphere without anything being taken away. The planet is essentially exhaling carbon dioxide and sulfur dioxide into its sky on a continuous basis, with no mechanism to ever breathe them back in. This also means the surface of Venus is not the ancient, frozen landscape scientists long assumed. It is being reshaped, slowly but continuously, by fresh lava flows. New rock is being laid down, old features are being buried. The planet's surface is a work in progress, a canvas that is still being painted. And then, in February 2026, the story took yet another unexpected turn. The surprises from Venus were coming faster now, each one building on the last, each one revealing a planet more complex and more active than anyone had imagined. A team of researchers at the University of Trento in Italy, led by geoscientists who specialize in radar analysis of planetary surfaces, published a paper in Nature Communications that described something no one had expected to find: a lava tube beneath the surface of Venus. Lava tubes are underground channels created when the outer surface of a flowing lava stream solidifies while the interior continues to flow. When the eruption ends and the interior drains, what remains is a hollow tunnel, sometimes extending for miles. They are common on Earth. They exist on the Moon, where several collapsed skylights have been photographed from orbit. They have been proposed to exist on Mars based on surface features that suggest underground voids, but no one had seriously looked for them on Venus. The Trento team used a specialized technique to reanalyze Magellan radar data in the Nix Mons region of Venus. What they found was a surface feature consistent with a collapsed skylight, a place where the roof of an underground lava tube had partially caved in, revealing the void beneath. The data suggested the tube was approximately 1 kilometer wide. The roof was at least 150 meters thick, and the void was at least 375 meters deep. These dimensions are enormous. The largest known lava tubes on Earth, in places like Iceland, Hawaii, and the Canary Islands, are typically a few tens of meters wide. Lunar lava tubes, based on the Grail gravity data and orbital imaging, could be significantly larger, potentially hundreds of meters across. But the Venus tube, if confirmed, would be among the largest subsurface voids discovered on any rocky body in the solar system. There is a physical reason Venus might support larger lava tubes than Earth. Venus's lower gravity, about 90% of Earth's, means that the rock forming the roof of a tube experiences less downward force, allowing wider spans to remain structurally stable. Additionally, Venus's dense atmosphere creates higher surface pressures, which can also contribute to the stability of underground voids, and the pervasive heat of the Venusian surface, while destructive to spacecraft and unfriendly to life, may actually help preserve the structural integrity of lava tubes by keeping the rock warm and somewhat plastic, reducing the likelihood of brittle fracture and collapse. The discovery matters for several reasons beyond the sheer novelty of finding a subsurface structure on another planet. Lava tubes are direct evidence of sustained volcanic flows. They do not form from brief explosive eruptions. They form when lava flows steadily for an extended period, long enough for the outer surface to cool and solidify while the interior continues to move. When the eruption eventually stops and the interior drains, the result is a hollow tunnel that can persist for geological ages. The existence of a kilometre-wide lava tube beneath Nix Mons means that region experienced not just occasional eruptions, but sustained, significant lava flows capable of carving out underground channels of extraordinary size. That speaks to a volcanic history that is rich, prolonged, and energetically substantial. The fact that the tube appears to still be partially intact, with a recognisable skylight where the roof has collapsed, suggests it is not geologically ancient. Very old tubes tend to be filled with debris, obscured by subsequent volcanic activity, or crushed by the gradual settling of rock over millions of years. A tube with a visible unfilled void suggests relative geological youth. Lava tubes also matter for the future of planetary exploration in ways that extend beyond Venus. On the Moon and Mars, lava tubes have been proposed as potential shelters for human habitation. They offer natural protection from radiation, micrometeorites, and the extreme temperature swings of worlds without thick atmospheres. On Venus, the surface conditions are so extreme that human habitation is not remotely feasible with any technology that exists or is likely to exist in the near term, but lava tubes could provide scientifically valuable windows into the planet's subsurface. Future missions equipped with subsurface radar, such as the European Space Agency's upcoming Envision orbiter, could map these structures from orbit, revealing the volcanic plumbing system of an entire planet in a way that has never been done before. There is even speculation, admittedly, at the far edges of what scientists are willing to discuss on the record, that subsurface voids on Venus might offer conditions significantly different from the hellish surface. Deeper underground, temperatures and pressures would be different. The composition of trapped gases might differ from the atmosphere above. Whether such environments could be relevant to any discussion of habitability is unknown, but the mere existence of large, stable underground voids adds another dimension of complexity to a planet that was supposed to be simple. Taken together, the volcanic discoveries of 2023, 2024, and 2026 paint a picture of Venus that is radically different from the one in the textbooks just a few years ago. This is not a dead world. This is not a planet that experienced its last gasp of geological activity hundreds of millions of years ago and has been cooling quietly ever since. Venus is alive, its volcanoes are erupting, its surface is being reshaped, its atmosphere is being fed by fresh volcanic gases on timescales of years and decades, and beneath that surface a network of underground channels reveals a volcanic history that is complex, dynamic, and far from over. Understanding why this matters requires thinking about Venus as a system, not just a collection of isolated features. The volcanoes feed the atmosphere traps heat, the heat affects the surface geology in turn influences the volcanism. It is a feedback loop, and it is running right now. Venus is not frozen in time, it is a planet in motion. The volcanic discoveries were surprise enough. They forced scientists to reconsider fundamental assumptions about Venus's geology and climate. But then, just a few years before Herrick found his volcano, a team of astronomers announced something that made the volcanic discoveries look almost mundane by comparison. Something that didn't just rewrite the geology textbook, it questioned the biology textbook too. In September 2020, a team of astronomers led by Jane Greaves of Cardiff University published a paper in Nature Astronomy that landed like a bomb in the scientific community. Using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, Greaves and her colleagues reported the detection of phosphine gas in the clouds of Venus. Phosphine, pH 3, a simple molecule, one phosphorus atom bonded to 3 hydrogen atoms. On Earth, phosphine is produced almost exclusively by biological processes. Anaerobic bacteria, organisms that thrive in environments without oxygen, produce phosphine as a metabolic byproduct. It is found in swamps, in the intestines of animals, in the sewage sludge of wastewater treatment plants. It is, in the language of astrobiology, a potential biosignature, a gas whose presence might indicate the activity of living organisms. To be clear about what the team was and was not claiming, they did not announce the discovery of life on Venus. What they announced was the detection of a gas that, as far as anyone knows, should not be present in Venus's atmosphere in the quantities they measured, approximately 20 parts per billion, unless something unexpected is producing it. They systematically went through every known, non-biological process that could generate phosphine on a rocky planet: lightning, volcanic outgassing, meteorite, delivery, photochemical reactions in the atmosphere. None of them could account for the observed concentration, not even close. The chemistry simply did not work. Known abiotic processes could produce at most a few parts per trillion. The detected signal was roughly 10,000 times larger. The implication was breathtaking in its simplicity. Either there is a chemical process on Venus that no one has yet identified, something completely new to planetary chemistry, or there are organisms in the clouds of Venus producing phosphine the same way organisms on Earth do. The scientific community reacted with a mixture of excitement and deep skepticism, which is exactly what should happen when an extraordinary claim is made. Several teams immediately began reanalyzing the data, questioning the telescope calibrations, challenging the spectral line identification, and proposing alternative chemical pathways. The debate was fierce, rigorous, and exactly the kind of scientific pushback that makes the process work. One group, led by Ignace Snellen at Leiden Observatory in the Netherlands, argued that the spectral feature Greaves had attributed to phosphine could be contaminated by sulfur dioxide, a gas known to be present in Venus's atmosphere at much higher concentrations. If the sulfur dioxide signal had leaked into the phosphine measurement, the apparent detection could be an artifact. Greaves responded by reanalyzing the data with updated calibration methods and arrived at a lower but still significant concentration of approximately 5 to 7 parts per billion. The detection held, though it reduced confidence. Another team questioned whether the James Clark Maxwell telescope data had been properly calibrated, noting that a software error in the data processing pipeline had introduced spurious spectral features that could mimic the phosphine signal. The Greaves team acknowledged the issue, corrected the calibration, and reprocessed the data. The phosphine signal survived the correction, though again at lower statistical significance than the original announcement. As of now, the phosphine detection remains contested but not refuted. Multiple reanalyses have reduced the initial estimate of 20 parts per billion to something in the range of 1 to 7 parts per billion. Some scientists consider the detection robust at this lower level. Others argue it is below the threshold of reliable measurement for these instruments. The debate continues. What is perhaps most fascinating about the phosphine controversy is what it reveals about the limits of ground-based astronomy when applied to Venus. Earth's own atmosphere contains trace amounts of phosphine, produced by the biological and industrial processes on the planet's surface. When observing Venus from Earth, the telescope's signal must pass through our own atmosphere, and distinguishing Venusian phosphine from terrestrial phosphine contamination is a delicate exercise in data processing. The James Clark Maxwell telescope observes at submillimeter wavelengths, where the spectral line of phosphine sits near lines of sulfur dioxide and other molecules. Separating these overlapping signals requires sophisticated mathematical techniques, and different teams applying different methods have reached different conclusions from the same raw data. This is not a failure of science. It is science working exactly as it should. Multiple independent groups testing the same claim from different angles, slowly converging on the truth through rigorous disagreement. the phosphine question will almost certainly not be resolved by ground-based observations alone. The definitive answer will require an instrument inside Venus's atmosphere, sampling the cloud layer directly, measuring phosphine concentrations without the interference of Earth's atmosphere or the ambiguity of distant spectral analysis. Da Vinci's mass spectrometer is designed to do exactly that. When the probe drops through the cloud layer, it will measure the concentration of phosphine and dozens of other trace gases with a sensitivity and precision that no telescope can match. If phosphine is there at the levels Greaves reported, Da Vinci will find it. If it is not there, Da Vinci will establish an upper limit that settles the debate. Until then, the phosphine controversy serves a purpose beyond its specific chemical question. It has drawn attention to Venus's atmosphere as a chemical system that we understand far less well than we assumed. The confidence that Venus's atmospheric chemistry was a solved problem, a known set of reactions involving sulfur, carbon and oxygen compounds cycling predictably through the atmosphere, has been shaken. There are anomalies, unexplained chemical species, reactions that should not be happening. The phosphine, whether or not it is ultimately confirmed, was the catalyst that forced the community to acknowledge those anomalies and take them seriously. But what has been less controversial, and arguably more interesting, is the work that the phosphine announcement catalyzed. Regardless of whether the original detection stands or falls, it forced scientists to take a hard look at Venus's atmosphere and ask a question that most had never seriously considered. Could the clouds of Venus support life? The answer, surprisingly, is not an automatic no. The clouds of Venus exist in a layer between roughly 30 and 43 miles above the surface. At these altitudes, conditions are dramatically different from the hellish surface below. The temperature at 33 miles altitude is roughly 140 degrees Fahrenheit. Warm, certainly, but not unimaginably so. There are microorganisms on Earth, extremophils, that thrive at temperatures well above 200 degrees Fahrenheit, in hydrothermal vents and volcanic hot springs. The atmospheric pressure in the cloud layer is close to 1 atmosphere, nearly identical to the pressure at sea level on Earth. And while the cloud droplets are made of concentrated sulfuric acid, roughly 85% sulfuric acid by weight, even this is not an automatic death sentence for life. Extremophil organisms on Earth survive in environments with pH values near zero, essentially pure acid. Jane Greaves' colleague Sarah Seeger at MIT, one of the world's leading experts on exoplanet atmospheres, had been thinking about the possibility of life in Venus's clouds even before the phosphine announcement. Together with her collaborator William Baines, a biochemist, Seeger developed a hypothetical life cycle for Venusian aerial organisms. In their model, microbes would inhabit the cloud droplets themselves, living inside the sulfuric acid droplets, the way certain bacteria on Earth live inside water droplets in clouds. As the cloud droplets grow and settle downward, the microbes would enter a dormant phase, essentially drying out into spores as they fall below the cloud layer into hotter, drier regions. Updrafts would then carry them back up into the clouds, where they would rehydrate, reactivate, and resume their metabolic activity. It is an aerial life cycle with no surface phase at all. The organisms would live, reproduce, and die entirely within the clouds. Is this plausible? The honest answer is, we do not know. It is not physically impossible. Each individual step, microbial life in acid, dormancy during transport, reactivation in favourable conditions, has analogues on Earth. But chaining them all together on another planet, in an atmosphere that is chemically different from anything on Earth, is a leap that requires evidence, not just analogy. It is worth dwelling for a moment on just how different the chemical environment of Venus's clouds is from anything on Earth. On our planet, life exists in water. Every known living organism, without exception, uses liquid water as its solvent, the medium in which its biochemistry operates. The chemistry of life on Earth is water chemistry. Proteins fold in water, DNA replicates in water, cell membranes form in water, metabolism occurs in water. When astrobiologists search for life on other worlds, they almost always search for water first, because no one has ever demonstrated that life can operate in any other solvent. Venus's clouds do not contain liquid water, they contain concentrated sulfuric acid, one of the most corrosive substances known. At 85% concentration, the sulfuric acid in Venus's cloud droplets would dissolve most organic molecules on contact. It would denature proteins. It would strip apart the molecular structures that form the basis of all known biochemistry. If life exists in Venus's clouds, it either has biochemistry radically different from anything on Earth, biochemistry based on sulfuric acid rather than water, or it has developed extraordinary protective mechanisms that shield its water-based chemistry from the acid environment, perhaps enclosed in some kind of acid-resistant membrane, or embedded within solid particles that prevent contact with the surrounding liquid. Both possibilities would be extraordinary. The first would mean that life can arise in solvents other than water, which would have staggering implications for the search for life throughout the universe. The second would mean that life can evolve solutions to chemical challenges so extreme that they would seem impossible if we had not found evidence of them. What made the debate even more interesting was a series of laboratory studies that began after the phosphine announcement. In 2024, a team at MIT led by Maxwell Seeger, Sarah Seeger's son, published results showing that 19 out of 20 biogenic amino acids, the building blocks of proteins, are stable in concentrated sulfuric acid at Venus cloud conditions. The amino acids did not dissolve, they did not decompose, they survived. This was not proof of life. It was proof that one of the fundamental requirements for life as we know it, stable amino acids, is not ruled out by Venus's cloud chemistry. In early 2025, a team led by Janusz Petkowski, also in Sarah Seeger's group at MIT, published an even more provocative finding. They demonstrated that peptide nucleic acid, or PNA, a molecule structurally similar to DNA but chemically distinct, is not only stable in concentrated sulfuric acid, but actually reacts in ways that could facilitate information storage and replication. PNA had long been proposed as a possible precursor to DNA and RNA in the origin of life on Earth. The discovery that it behaves in interesting and potentially functional ways in sulfuric acid opened an entirely new line of speculation about what Venusian biochemistry might look like if it exists at all. And then there were the lipids. In another 2025 study from the Seeger lab, researchers showed that simple lipid molecules, the building blocks of cell membranes, can form stable higher order structures in concentrated sulfuric acid. On Earth, lipids spontaneously organize into membranes that enclose cells, creating the boundary between the inside and outside of a living organism. The discovery that lipids can form similar organized structures in sulfuric acid raised the possibility that cell-like compartments could in principle exist in Venus's clouds. None of this proves that life exists on Venus. It proves something more subtle and, in its own way, more important, that the chemistry of Venus's clouds does not automatically preclude life. The amino acids can survive, the nucleic acid analogues can function, the lipids can organize. The building blocks are compatible with the environment. Whether anything has ever actually assembled those building blocks into a living system in Venus's clouds is a question that can only be answered by going there and looking. The phosphine debate opened another door as well. It drew attention to a mystery that had been quietly nagging at Venus scientists for nearly a century. the unknown ultraviolet absorber. When you look at Venus in visible light, it is a featureless white sphere, bright and beautiful and completely uninformative. But when you look at Venus in ultraviolet light, a dramatic transformation occurs. Dark patches and streaks appear in the cloud tops, concentrated primarily in a band near the equator. Something in the upper clouds is absorbing enormous amounts of ultraviolet radiation, roughly half of all the solar energy that Venus absorbs. This substance, whatever it is, plays a central role in Venus's energy budget. It is one of the primary drivers of the planet's atmospheric dynamics. The super-rotation of the upper atmosphere, the global wind patterns, the temperature distribution, all of these are influenced by where and how this mysterious substance absorbs solar energy. And no one knows what it is. The absorber was first noticed in ultraviolet photographs of Venus taken in the 1920s. For over 100 years, scientists have been trying to identify the substance responsible. The leading candidate for decades was concentrated sulfuric acid. But sulfuric acid does not absorb ultraviolet light at the right wavelengths to explain the observations. Iron chloride has been proposed, so has elemental sulfur. Various allotropes of sulfur, molecules made of different numbers of sulfur atoms bonded together, can absorb UV light in the relevant range. In 2016, a study proposed that the absorber might be iron-bearing sulfite minerals mixed into the cloud droplets. Another study suggested it could be a sulfur polymer produced by photochemical reactions high in the atmosphere. Each proposal explains part of the absorption spectrum, but not all of it. No single substance has been identified that matches the full range of observed UV absorption. The difficulty of identifying the absorber speaks to a broader challenge in Venus science. We have remarkably little direct data from the cloud layer itself. The Soviet Venera probes descended through the clouds, but their instruments were not designed to characterize cloud particle composition in detail. They were focused on getting to the surface alive. The Vega balloons floated within the cloud layer for 46 hours, but their instrument packages were limited in what they could measure. Venus Express and Akatsuki have observed the clouds from orbit, but remote sensing from above can only reveal so much about the composition of particles embedded within a thick, opaque cloud deck. The UV absorber has been studied almost entirely through indirect methods: spectral analysis from orbit, polarimetry, and theoretical chemistry, rather than through direct sampling. It is as if scientists were trying to identify the ingredients of a soup by smelling the steam from across the room. You can learn something, but you cannot be certain. And then there is the possibility that the absorber is biological. Certain microorganisms on Earth produce pigments that absorb UV light. If microbes exist in Venus's clouds, they might produce similar pigments, either as a form of sunscreen to protect their cellular machinery from UV damage, or as a way to harvest solar energy for metabolism. The UV absorber's spatial distribution, concentrated in bands near the equator where solar irradiation is strongest, is at least loosely consistent with what you might expect from a photosynthetic or photoprotective biological community. This is speculation. It is clearly labelled as such by the scientists who propose it. But it is not fringe speculation. It is a hypothesis that appears in peer-reviewed papers, discussed at international conferences, and taken seriously enough that upcoming missions are being designed in part to test it. The Venus Express orbiter, during its 9 years in orbit from 2005 to 2014, collected extensive data on the UV absorber's distribution and temporal variability. The absorber is not static. Its distribution changes over timescales of days to weeks. Some regions become darker, while others lighten. The patterns shift and evolve. This variability has proven difficult to explain with purely chemical models. Photochemical processes tend to produce fairly uniform distributions, not the patchy, shifting patterns observed. Volcanic eruptions could inject absorbing material into specific regions, but the patterns do not correlate well with known volcanic locations. The variability remains unexplained. Da Vinci, when it descends through Venus's atmosphere, will pass through the cloud layer where the UV absorber operates. Its instruments will measure the chemical composition of the cloud droplets and surrounding gas with a precision that no previous mission has achieved. If the absorber is a known chemical compound, Da Vinci should identify it. If it is something new, something not in any spectroscopic database, that finding alone would be extraordinary. The UV absorber is one of those scientific mysteries that has been hiding in plain sight for a century. It absorbs half of all the solar energy that drives an entire planet's climate. It creates the dramatic patterns visible in every UV image of Venus. It influences the global atmospheric circulation. And after 100 years of observation, we still cannot identify what it is. In almost any other context, a substance responsible for half of a planet's energy absorption would be the top scientific priority. On Venus, it has been treated as an interesting footnote, mostly because Venus itself was treated as a footnote for so long. That is changing now. The UV absorber, the phosphine question, the volcanic activity, the cloud chemistry. These are all pieces of a single interconnected puzzle, and the puzzle is attracting the attention it has long deserved. But behind all of these individual mysteries lies a bigger question, a question that connects the volcanoes, the phosphine, the UV absorber, the cloud chemistry and the surface conditions into a single unified narrative. It is the question that makes Venus not just scientifically interesting, but scientifically urgent. Was Venus ever habitable? Did it once have liquid water, oceans, moderate temperatures and conditions that could have supported life? The idea is not new. It goes back to the 1960s when scientists first began to suspect that Venus's runaway greenhouse effect might not have been the planet's original state. The reasoning was simple. Venus formed from the same material as Earth, at roughly the same distance from the Sun. It should have received roughly similar amounts of water during its formation. If Earth's water survived and formed oceans, why wouldn't Venus's? The modern version of this idea was most thoroughly developed by Michael Way and Anthony Del Genio at NASA's Goddard Institute for Space Studies. In a series of papers published between 2016 and 2020, Way and Del Genio used sophisticated climate models to simulate Venus's history under a range of different assumptions about its early atmosphere, its water content, and its rotation rate. Their findings were remarkable. In their models, a slowly rotating Venus with an Earth-like atmosphere and modest water inventory could maintain liquid water oceans on its surface for up to 3 billion years. The slow rotation, paradoxically, was an advantage. It created a thick layer of clouds on the sunlit side of the planet that reflected solar radiation back into space, keeping surface temperatures moderate despite Venus's proximity to the Sun. The clouds acted as a global sunshade. In some of their simulations, Venus's average surface temperature remained below 140 degrees Fahrenheit for billions of years, warm but not uninhabitable, a hot spring world, challenging but not dead. If these models are correct, then for most of Venus's history, it may have been a planet with shallow oceans, humid clouds and temperatures that a sufficiently hardy organism could survive. Life might have originated there, or it might have been delivered from Earth via meteorites, a process called panspermia that has been proposed as a mechanism for seeding life between nearby planets. Either way, the model suggested that Venus had time, billions of years of time for life to take hold. But then something changed. Something triggered the runaway greenhouse effect that turned Venus from a potentially habitable world into the inferno it is today. The Weyandel Genio model suggested this trigger might have been a massive volcanic event, a global resurfacing episode that released enormous amounts of carbon dioxide into the atmosphere in a geologically short period. Once the CO2 concentration crossed a critical threshold, the positive feedback loop kicked in. More heat, more evaporation, more water vapour in the atmosphere trapping more heat, more evaporation. The oceans boiled away, the water vapour rose into the upper atmosphere, where ultraviolet radiation broke it apart. The hydrogen escaped to space. The oxygen was consumed by surface reactions. Within a few 100 million years, every drop of water was gone. Not everyone was convinced. In 2023, a team led by Alexandra Warren and Edwin Kite at the University of Chicago published a paper in the Proceedings of the National Academy of Sciences that pushed back hard against the habitable Venus hypothesis. Warren and Kite focused on a specific problem. If Venus once had oceans that evaporated, where did all the oxygen go? Water is H2O. When you break it apart, you get hydrogen and oxygen. The hydrogen, being lightweight, can escape to space, but oxygen is heavier, much heavier. If Venus's oceans evaporated and the water molecules were split by ultraviolet radiation, the hydrogen would have escaped, but a vast quantity of oxygen should have been left behind. Warren and Kite calculated how much oxygen this would have produced, and then asked what happened to it. On Earth, free oxygen is consumed by oxidizing surface rocks, by reacting with volcanic gases, and by biological processes. On Venus, without plate tectonics to continuously expose fresh rock, the primary sink for oxygen would have been the oxidation of the surface and reactions with volcanic emissions. Warren and Kite modelled these processes and concluded that Venus could not have disposed of all the oxygen fast enough to match the current's atmospheric composition, which contains very little free oxygen. Their modelling suggested that either Venus started with far less water than the optimistic models assumed, or the water was lost very early in the planet's history, before it could accumulate into substantial oceans. Their work did not rule out the possibility of habitable Venus entirely. It narrowed the window. If Venus had oceans, they had to have been smaller and shorter-lived than the Weyandel Genio model suggested. The debate between these two views remains active. Then in late 2024, a third team entered the debate with evidence that pushed even further against the habitable Venus hypothesis. Teresa Constantinou and Oliver Shortall at the University of Cambridge, working with Paul Rimmer, published a study in Nature Astronomy that approached the question from a completely different angle. Rather than modelling the climate or running simulations of atmospheric evolution, they looked at the chemistry of Venus's current atmosphere and asked what it could tell them about the planet's interior. Their reasoning was elegant. On Earth, the composition of volcanic gases reflects the composition of the mantle rock that produces them. Wetter mantles produce different volcanic emissions than drier ones. By analysing the chemical equilibrium of Venus's atmosphere, particularly the ratios of gases that are sensitive to the water content of the source rock, Constantinou and Shortall calculated how much water Venus's interior contains today. Their conclusion was stark. Venus's interior is exceptionally dry, far drier than Earth's mantle, dry enough that the planet may never have had sufficient water to form substantial oceans in the first place. The logic runs like this. If Venus once had significant oceans that evaporated, some of that water would have been recycled into the planet's interior through geological processes, even without Earth-style plate tectonics. Hot rock interacts with water. Water gets incorporated into mineral structures. Over billions of years, at least some fraction of the surface water would have worked its way into the mantle. The fact that Venus's mantle appears to be so dry today suggests that there was never much water there to begin with. This argument complemented Warren's missing oxygen problem with an entirely independent line of evidence. Warren asked where the oxygen went if the oceans evaporated. Constantinou asked where the water went if oceans ever existed. Both questions pointed in the same uncomfortable direction. Perhaps Venus was never the watery twin of Earth that the optimistic models had suggested. The Cambridge study did not claim to have settled the question definitively. The authors acknowledged that their analysis depends on assumptions about how Venus's atmosphere and interior have interacted over billions of years, and those interactions are not fully understood. It is possible that processes we have not yet considered could reconcile a dry present-day interior with a wet past, but the study added significant weight to the case that Venus's habitability may have been far more limited than the most hopeful scenarios suggest. What Da Vinci will be able to contribute to this debate is direct measurement of noble gases in Venus's atmosphere, particularly the ratios of different argon and xenon isotopes. Noble gases are chemically inert. They do not participate in reactions, they simply accumulate. Their isotopic ratios act as a kind of geological clock, recording information about a planet's volcanic history and the rate at which its interior has degassed over time. On Earth, noble gas measurements have revealed fundamental information about the planet's formation and the history of its atmosphere. On Venus, no mission has ever measured noble gas ratios with sufficient precision to constrain the models. Da Vinci will. In 2025, a team led by Matthias Green at Bangor University in Wales, working with NASA collaborators, proposed an entirely new piece of the puzzle. Green is an oceanographer, not a planetary scientist, and his contribution came from applying ocean science to planetary history. Green's insight was about tides. If Venus once had liquid water oceans, those oceans would have experienced tidal forces from the sun, much as Earth's oceans experience tides from the moon. Tidal friction transfers energy from a planet's rotation to its oceans, gradually slowing the planet's spin. On Earth, tidal friction from the moon is slowing our rotation by about 2.3 milliseconds per century, so gradually that it is imperceptible to human experience but significant over geological time. Green and his team modelled what would happen if Venus had oceans exposed to solar tides. Their simulations showed that the tidal braking effect on Venus would have been extremely powerful, far more powerful than the lunar tides on Earth, because the sun's gravitational influence on Venus is much stronger than the moon's influence on Earth due to Venus's proximity to the sun. In their models, solar tides could have slowed Venus's rotation from an initially fast spin to its current near standstill in approximately 1 to 2 billion years. This is significant because it provides a potential mechanism for one of the most puzzling aspects of Venus's history. Venus rotates extremely slowly now. One Venus day takes 243 Earth days. If Venus once rotated much faster, something had to slow it down. A giant impact could do it. Solar tidal effects on its thick atmosphere could contribute. But ocean tides, if they existed, would have been the dominant braking force. The implications cascade. If ocean tides slowed Venus's rotation, and if Venus's slow rotation is what prevents the planet from generating a magnetic field, and if the lack of a magnetic field is what allowed the solar wind to strip away Venus's water, then the oceans themselves may have been the instruments of their own destruction. The water created the tides. The tides slowed the rotation. The slow rotation killed the magnetic field. The dead magnetic field exposed the atmosphere to the solar wind. The solar wind helped destroy the water. It is a feedback loop of extraordinary elegance and cruelty. If it is correct, Venus's oceans did not simply evaporate because the sun was too close. They were actively involved in the chain of events that led to their own annihilation. They sowed the seeds of their own destruction simply by existing. This idea remains speculative. It depends on Venus having had oceans in the first place, which is precisely the question that the Warren and Constantino teams have challenged. But it illustrates the depth and interconnectedness of the Venus puzzle. Every feature of the planet connects to every other feature. The rotation connects to the magnetic field, connects to the water loss, connects to the greenhouse effect, connects to the volcanism, connects to the atmosphere. Understanding Venus requires understanding all of it, simultaneously, as a single system. And that is exactly what the upcoming missions are designed to do. For the first time in over 3 decades, we are going back to Venus, not with one mission, but with several. Launched by multiple space agencies designed to answer questions that scientists did not even know to ask when the last missions flew. NASA's Da Vinci mission, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, will send a probe plunging through Venus's atmosphere. The descent will take roughly 1 hour, during which the probe will measure the chemical composition of the atmosphere at every altitude, from the cloud tops to the surface. It will measure noble gas isotope ratios with precision that no previous mission has achieved. It will sample the cloud droplets and analyze their composition. It will take infrared images of the Tessera terrain as it descends, capturing the first close-up images of Venus's oldest geological features. And if it survives impact, which is not guaranteed but is possible, given the thick atmosphere's braking effect, it may transmit data from the surface for a few precious minutes. Da Vinci is currently scheduled for launch in the early 2030s. NASA's Veritas mission, which stands for Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, will orbit Venus and map its surface using radar at resolutions far exceeding anything Magellan achieved. Veritas will measure surface topography, detect ongoing volcanic activity through changes in surface features over time, and map the composition of surface rocks using near-infrared spectroscopy. It will image the Tessera terrain at resolutions that could reveal whether those ancient, deformed rocks preserve evidence of past plate tectonics. Veritas will, in effect, give scientists the equivalent of what Magellan gave them in the 1990s, but orders of magnitude more detailed. The European Space Agency's Envision Orbiter is another radar mapping mission, but with different instruments and different scientific priorities. Envision carries a subsurface radar sounder capable of probing beneath the Venusian surface, potentially revealing underground structures like the lava tubes discovered in the 2026 study. It also carries instruments to study the atmosphere from orbit, including spectrometers designed to measure trace gases that could reveal ongoing volcanic emissions. Envision and Veritas will complement each other, providing overlapping but distinct data sets that together will create the most comprehensive picture of Venus's geology and atmosphere ever assembled. And then there is Rocket Lab, the private launch company, which has announced plans for a small atmospheric probe of its own. The mission, backed in part by the Venus Life Foundation, would send a tiny spacecraft through Venus's clouds to sample the cloud droplets and look for organic chemistry. It is smaller and simpler than Da Vinci, but it could launch sooner, potentially providing the first new atmospheric measurements of Venus in over 40 years. There are also proposals that have not yet been funded, but are under serious discussion. A Venus balloon mission that would float for weeks or months in the cloud layer, continuously sampling the atmosphere and monitoring changes in chemistry, temperature and wind patterns. A long-duration surface lander using advanced electronics based on silicon carbide, a semiconductor material that can operate at Venus surface temperatures without the need for cooling, potentially surviving for months instead of minutes. A seismic network that would listen for Venus quakes through atmospheric pressure waves, revealing the planet's internal structure without ever touching the ground. Whether all of these missions fly, or only some of them, or none of them in their currently proposed form, is a question of funding, politics, and the unpredictable currents of institutional decision-making. What is certain is that the scientific questions they are designed to answer have never been more urgent or more consequential, and the urgency extends far beyond our own solar system. One of the most profound shifts in Venus science over the past decade has been the recognition that Venus is not just a planet, it is a template, a reference case for understanding what is happening on rocky planets scattered across the galaxy, worlds we can see but cannot yet visit. The James Webb Space Telescope has opened a new era in exoplanet science, allowing astronomers to study the atmospheres of planets orbiting distant stars by analysing the light that filters through those atmospheres during transits. When a planet passes in front of its star, starlight is filtered through its atmosphere, and the chemical fingerprints of atmospheric gases are imprinted on that light. This technique, called transmission spectroscopy, has already been used to detect water vapour, carbon dioxide and other molecules on gas giant exoplanets. For rocky planets the signals are far fainter and the challenge far greater, but JWST is making it possible for the first time to probe the atmospheres of terrestrial worlds in and near the habitable zones of their stars. The problem is interpretation. When JWST detects carbon dioxide in the atmosphere of a rocky exoplanet, does that mean the planet is like Venus, a scorched world trapped in a permanent greenhouse? Or does it mean the planet is like early Earth, where carbon dioxide was abundant, but liquid water still existed? The two scenarios produce similar spectral signatures when observed from light years away. Distinguishing between them requires understanding exactly how Venus-like atmospheres differ from Earth-like atmospheres in their chemical details, which gases are present, which are absent, and in what ratios. Venus is the only example of a rocky planet with a thick carbon dioxide atmosphere that we can study up close. Every measurement made at Venus informs how astronomers interpret what JWST sees at distant worlds. In 2023, a team led by Colby Osberg at the University of California, Riverside, formalized a concept that had been developing in the exoplanet community for years: the Venus Zone. Just as the habitable zone describes the range of distances from a star where liquid water could exist on a planet's surface, the Venus Zone describes the range where a planet with an initially Earth-like atmosphere would experience a runaway greenhouse effect and evolve into a Venus-like state. The Venus Zone lies just inside the inner edge of the traditional habitable zone, a narrow band where a planet receives enough stellar energy to push it past the tipping point. The team catalogued over 300 confirmed rocky exoplanets orbiting within the Venus zone of their host stars and identified the 5 most likely candidates to be true Venus analogues based on their size, mass, density, and orbital distance. These planets are targets for JWST observation. If their atmospheres can be characterized, they would represent the first opportunity to study Venus-like worlds beyond our solar system, and to determine whether Venus's fate is common among rocky planets or an unusual outcome specific to our solar system's history. The implications are enormous. If Venus-like outcomes are common, then many planets currently counted as potentially habitable may actually be hellish. The habitable zone, as traditionally defined, may be significantly narrower than astronomers have assumed. On the other hand, if Venus-like outcomes are rare, it would suggest that there is something unusual about our Venus, some specific feature of its history or composition that pushed it toward catastrophe, while other planets in similar orbital positions remain temperate. This is why the habitability debate matters so much. If Wey's models are correct, and Venus maintained habitable conditions for billions of years before a volcanic catastrophe triggered the runaway greenhouse, then Venus-sown planets elsewhere might also be habitable for long periods. They would be worlds worth studying for signs of life. If Warren and Constantinu are correct, and Venus was never truly habitable, then Venus-sown planets are likely dead ends for the search for life, and the habitable zone is truly a narrow corridor in which Earth sits close to the centre. Venus is no longer just a planet. It is a Rosetta Stone for understanding the billions of rocky worlds that orbit other stars. What we learn at Venus determines how we read the data coming back from JWST. It determines which exoplanets we prioritise for study. It determines ultimately how many worlds we consider capable of supporting life. The stakes could not be higher, and the answers are all waiting at a planet that sits, on average, only 26 million miles away. There is one more thing to say about Venus. One more perspective that is worth holding as you think about everything we have discussed. Venus is Earth's twin. Not metaphorically, physically. The same size, the same mass, the same basic composition, formed in the same cloud of gas and dust at the same time in the same solar system. For the first few 100 million years after their formation, the two planets may have been essentially indistinguishable. Two rocky worlds, cooling, outgassing, developing atmospheres, possibly developing oceans, two siblings. And then, at some point their paths diverged. Earth stayed habitable. Venus did not. The question of when and why that divergence happened is one of the most important questions in all of science, because it speaks directly to the resilience of habitability itself. Is Earth's continued capacity to support life a robust, stable state that would be difficult to disrupt? Or is it a fortunate accident, a delicate balance that could tip at any moment if the right conditions were perturbed? Venus suggests the latter. Here is a planet that started with nearly everything Earth had, and it ended up with surface temperatures that melt metal and clouds made of acid. The margin between Earth and Venus may not be as wide as we would like to think. This is not a story about a distant alien world. It is a story about a road not taken. A story about the planet that Earth could have become, and perhaps under different circumstances still could. The distance between a world of oceans and a world of fire is smaller than we ever imagined. Understanding that distance, measuring it, characterizing it, knowing exactly which variables separate one fate from the other, is not just a scientific exercise, it is an existential one. The probes are being built, the telescopes are being aimed, the questions have been formulated. For the first time in a generation, humanity is preparing to return to Venus with instruments capable of answering questions that have been waiting patiently for decades. Venus has been hiding its secrets behind those bright white clouds for 4.5 billion years. We have spent less than 60 years looking, and already, in that tiny fraction of the planet's lifetime, we have discovered active volcanoes, impossible chemistry, a century-old atmospheric mystery, laboratory evidence that the building blocks of life can survive in those acid clouds, and mounting evidence that the planet's history is far more complex and far more relevant to our own than anyone suspected. The next chapter of the Venus story will be written by the spacecraft that are being built right now in clean rooms and engineering labs on Earth. When those missions arrive, when Da Vinci drops through the clouds, when Veritas maps the surface, when Envision peers beneath the ground, we will learn things about Venus that will surprise us. That is one prediction that is safe to make. Venus has been surprising us for centuries. There is no reason to think it will stop now. And somewhere in those surprises may be the answer to the question that haunts all of planetary science. The question that Venus poses simply by existing, simply by being so similar to Earth in its origins and so different in its outcome. How fragile is a habitable world? We do not know yet, but we are closer to finding out than we have ever been. And the answer, whatever it turns out to be, will come from a planet that has been shining in our evening sky since the very first human looked up and wondered what that bright light was. Venus, the morning star.